This construction method is based on experience gained in the 60s, when expanded polystyrene slabs were used for the first time in road construction for frost protection. Particularly in countries with severe winters, such as in alpine regions, in North America and in Scandinavia, this type of construction gained significance. In Norway in 1972, the first road embankments using expanded polystyrene were built. It was from there that trade interest was aroused in many countries for this type of construction. The Geofoam construction method with expanded polystyrene foam, known for short as EPS, has ever since been applied successfully as the economic alternative in the construction of roads over ground unable to bear heavy loads. The advantage of expanded polystyrene, such as styropor foam, lies in its low bulk density. At a density of 15 to 20 kilograms per cubic meter, the weight amounts to only 1/100th of the usual embankment material. Consolidation of the subsoil is reduced accordingly. Styropor foam resists aging and does not act as a nutrient medium for microorganisms. The closed cell structure means that water absorption is very low. Styropor foam is moisture resistant, biologically safe, and unable to endanger the groundwater. There are lots of test results from various countries on the weight-bearing capacity of the geofoam construction method, as well as long-term practical experience. In order to gather its own data on this method of construction, the Federal Institute for Highway Systems carried out comparative studies on an experimental road. At a 3-meter deep major test site, unfavorable ground conditions such as silt layer deposits and irrigation were simulated. Expanded polystyrene blocks were laid out in 2 layers to form a 1-meter thick geofoam foundation. The subsequent layers of the road were built on top of that. 3 different structures were tested using the same thickness of cover layer in all cases. In the first version, a thin plate of concrete was used to strengthen the structure. In the second version, the covering consisted solely of loose gravel. In the third version, compacted sand was placed on top of the blocks. The tests included examination of the material itself, as well as numerous measurements during construction and later of the finished road sections. The marked sections of varying structure were separated from one another. Important aspects of the tests were over-travel measurements with realistic loads and constant load trials with impulse generators. The impulse generators are applied lengthways and laterally in order to simulate genuine traffic loads. This enabled the testing of the geofoam construction method whilst arriving at evaluations of the various versions of structure. In several countries, the geofoam construction method has already been included in control standards. Both experience gained abroad and the results gained from trials conducted at the FIHS led also in Germany to the issuing of recommendations for the planning, invitation for tenders and actual construction of roads. Let us look at an example of this. Emden's Western Bypass. Increasing traffic volume could not be borne by the existing road, so 2 additional lanes were to be built, turning it into a motorway. The route crosses ground unable to bear heavy loads. Included in this project is a bridge secured by deep piles. The ramps were built on top of a 7-meter thick layer of peat bog. The level was expected to settle 2 meters as a result of the additional burden of the embankment's weight on the subsoil. The low weight-bearing capacity of the subsoil led to the decision to use styropor foam blocks as a lightweight building material. Settling at the edge of the bridge was thus avoided. The Federal Institute for Highway Systems carried out various tests for soil mechanics and set up measuring points. Here's a static tube sounding in the existing ground to establish its firmness. The trials were intended to facilitate comparisons with conventional construction methods. Delivery and laying of the styropor blocks proceed quickly. The 4-meter-long blocks are easy to handle. The first layer of blocks are merely laid on top of the prepared level of ground. Whilst the first layer is secured at the sides with filling material, the laying of the blocks continues. The blocks are fitted exactly alongside each other like building blocks. Clawed grips, as used in woodworking, serve to secure the blocks during construction. The end blocks are simply cut to size with a wire saw and fitted in place. The block layers are laid in opposite directions in order to avoid continuously vertical joints. As the individual layers are completed, the sides are continuously filled in so that the polystyrene is held firmly in place with filling material, which is compacted using light vibration machines. When the day's work is completed, not even a strong wind can shift the blocks out of place. The last layer of styropor blocks at this building site is covered with a layer of geofabric. The filling material, fine to medium-grain sand, is thus prevented from slipping into the narrow joints between the rigid foam blocks. The first layer of sand, directly on top of the styropor foam, is compacted with small vibration machines. The next layers above that are then again compacted with large vibration machines. This makes it possible to achieve compacting rates of over 98%. Altogether, the styropor blocks at this building site are arranged in 5 layers, each of 50 centimeters thickness, and covered with 1 meter of sand. The upper layer of the road was built in accordance with Building Category 3 of the Road Building Regulations 86, with 18 centimeters of asphalt over 15 centimeters of compacted sand. A few weeks later, the Federal Institute for Highway Systems conducted a load test on top of the finished asphalt layer. Before the flatbed trailer slowly approached the ramp, the zero norms for the unladen state of the road was first established. 11.5 tons per axle now bear down on the road surface and the embankment material of expanded polystyrene. Levelling instruments and precision apparatus are used to measure the impressions beneath the wheels of the vehicle. The result exceeded all expectations. The deformities on the surface are insignificantly small and lay within the range of the accuracy of the measurement. The measurements of the horizontal load on the thrust block and the pressure meter confirmed the positive effect of the expanded polystyrene. The light embankment construction material constitutes no horizontal pressure on the bridge abutments. After the load is removed, the minute vertical deformations disappear completely.